if we take a look at this infinite series, this infinite sum, 1 plus 1/2 plus 1/4 plus 1/8 and so on, there's a nice quick argument for saying that that has to be equal to 2. And if you've seen that before, that's good. If you haven't, you can take a look at my introduction to infinite series if you're interested in seeing why that's true. A similar series that we could look at, something like 2/3 plus 4/9 plus, and I'm just going to multiply each term by 2/3 to get the next term. So if we keep going like that, this also gives us a very specific number that we can write down. It's a finite number, and we can say exactly what it is. And with most series that you come across, you won't be able to say exactly what it's equal to. Hopefully you can determine whether it gives you something finite or something infinite, but being able to say exactly what it's equal to is a very special case. Both of these series are examples of something called a geometric series. We give it a special name because of these special properties. For both of these, to get each successive term, you're multiplying by the same ratio each time. That's what characterizes a geometric series. So we could write down a general geometric series as something like, it's often written as a constant that you start off with, I'll call it A, plus, and then you multiply that constant times your ratio. So here A is 1 and the ratio is 1/2. Here A is 2/3 and the ratio is also 2/3. But for each term you're just multiplying again by the ratio. So all the terms look the same, but you're just picking up an extra power of that ratio. There are certain conditions under which this gives you something finite and you can say exactly what it's equal to. So what I'm going to do is I'm going to stop this at a finite point. I'll say at the I'll say where r has a power of n. And I'll call that Sn. Sorry, this is a little messy. Sn stands for partial sum for me, and I'm thinking of the n as the power on the ratio. If I multiply this partial sum by a, then I get something that looks very similar to Sn itself. I'm sorry, I don't want to multiply by a. I want to multiply by the ratio r. If I do that, I get ar plus ar squared plus ar cubed, and so on. And my last one is going to have r to the n plus 1. Now what I'm going to do is subtract the second line from the first line. And when I do that, I get a lot of canceling going on here. I've got a positive AR and a minus AR, same for AR squared and so on, all the way down to AR to the n. So everything cancels out except for this A and this A times R to the n plus 1. So I'm going to write down an equation where I can get a nice expression for Sn. So my equation from this is Sn plus Rsn equals A plus A times R to the n plus 1. I want to solve for this Sn, and the reason I want to solve for that is because I really want to get my hands on the entire infinite series. And the definition of that infinite series is you take this partial sum that we started with here, and then you just take the limit of that as n goes to infinity. So this infinite series, it's not actually a sum, it's a limit of these partial sums. Alright, so I'm solving for Sn, I'm going to factor out Sn from the left side. That leaves me with a 1 plus r. And then I'll factor out an a from the right side just to analyze this a little more nicely. So what I have left over is 1 plus r to the n plus 1. Now I'm solving for Sn, so I divide both sides by 1 plus r. And to get the infinite series, which is what I really want an expression for, I'm just going to take the limit of this as n goes to infinity. And this is a nice compact expression, a nice finite object that I can deal with. I can analyze the limit, and then I can get an expression for this infinite series for a general geometric series. All right. So when I take that limit, first I'm going to use the summation notation for the geometric series. I'll write it like this. So this is just a compact way of writing out the infinite series. By definition, it's the limit of these partial sums. So I'm not going to write down the partial sum here. What I'm going to do is skip down to what we solved for here, this expression of a geometric series. And now it's worth taking a minute or two to pause and think about what this is actually equal to. I'll give you a hint if you want it before you pause. It has to do, well, it depends on the value of r. So, if you're ready to see how to figure this out, let's think about what happens as we let n go to infinity. What happens to this expression? I'm looking for a limit, so I'm thinking of a sequence of values that's limiting to some number, or that may go out to infinity. And you can see nothing is actually changing except for that r to the n plus 1. So what I really need to understand is, what is the limit as n goes to infinity of r to the n plus 1? So is that equal to something finite or not? Remember, r was the ratio that we were multiplying by. In the first series, we multiplied each successive term by 1/2, so r was 1/2. The next one, it was 2/3. If your ratio is between 0 and 1, then when you take this limit, those values will always be shrinking down to 0. So if you take a fraction, positive fraction, smaller than 1, and you multiply it by itself, you get something smaller than you started with. And if you keep that up forever, you're limiting down to 0. So this has a couple of possible answers. It's 0 if r is between 0 and 1. And by the way, I'm only thinking about positive values for the ratio right now. The other option, or I guess one other option, is we can let r equal 1, and then that means that for each successive term we're multiplying by 1, so all we're getting is the previous term. Then if your original term was 2/3 and then you keep multiplying by 1, you're doing 2/3 plus 2/3 plus 2/3 forever. That gives you something infinite. So if r is equal to 1, then r to the n plus 1, well, I guess that's equal to 1. If r is equal to 1. And then if r is bigger than 1, and you keep raising it to larger and larger powers, there's no limit to how big you'll get. So let's say this is equal to infinity. I mean, the limit diverges in this specific way. Or if the limit doesn't exist, in this specific way. So now, because I know this, it tells me what this is going to be equal to. So first, if we're in the case where r is between 0 and 1, like the two examples that I wrote on the board, then this r to the n plus 1 goes away, it turns into 0, and we're just left with a times 1 over 1 plus r. If r is equal to 1, then this expression doesn't make sense. If r is equal to 1, we know that the whole series is going to give us something infinite. So I'm going to hold on to that for a second. If r is greater than 1, then we get infinity here. And again, we know that that series is diverging because for each successive term, you're multiplying by something bigger than 1. So each term is bigger than the one before it. You're just growing forever, then adding those together. You definitely get something infinite there. Okay, I just realized that I wrote something down wrong earlier. I don't know at which point I made the mistake, but when I had Sn minus r to the, r times Sn, you may have caught this. When I factored out Sn, I got 1 minus r, and then on the right side it was that a times 1 plus r to the n plus 1. I don't know if it was when I wrote that down or when I just came over to here, but at some point I changed that on accident to a 1 plus r. So this plus should be a minus. And so what that tells me is that this case where r equals 1, for that case, this expression doesn't make sense. So I need to think about that one separately. And we thought about it separately, and we figured out that if you're multiplying each successive term by 1, you're adding the same thing infinitely many times. Your series diverges in that case as well. So now, let's just apply this real quick to the two examples that I wrote down on the board earlier. I'm going to write them out in their compact form. We had the sum of 1/2 to the k, where k started at 0. I'll write it like this as well. So here, you're starting out with 1. There's a hidden 1 right here. So a is equal to 1, and then r is 1/2. So we know from this expression that we got here that I'll have 1 over 1 minus r. So 1 over 1 minus 1/2. That's 1 divided by 1/2, which is 2. So that makes sense. The other one was 2/3 plus 4/9, and so on. There are a couple of different ways to write this. I could write this as 2/3 times 2/3 to the k, and start k at 0. So that when k equals 0, this says 2/3 times 1, so it's here. Or I could start this at k equals 1. So this would say 2/3 to the k. I'm starting at k equals 1, so I start with the 2/3. When you're using this formula for the answer to a geometric series, it always starts at k equals 0. So I want to either think about it this way, where a is 2/3 and r is 2/3, or I could calculate it this way, but if I do it this way, then I need to think of it as, what I need to do is calculate what would happen if you started at 1 and then just subtract 1 from that. So you could use a equals 1 and r equals 2/3 in this expression, but that assumes that you're starting with a 1 at the beginning. So whatever answer you would get from that, you would subtract 2/3 from it. Okay, here A is A is 2/3, and R is also 2/3. So we get 2/3 divided by 1/3. Which is also 2. This is kind of funny to me because I did not plan this at all. I did not expect this to be equal to 2. I just kind of picked a random ratio. But I guess what's happening here is you're starting out with a smaller value of A. I picked 2/3 here instead of 1. And then I'm using a bigger ratio, and it just happened to be the case that the smaller A that I picked and then the bigger ratio that I picked balanced each other out perfectly so that these two are equal to each other.